The next thing I want to do is show you a general attack on collision-resistant hash functions. If you remember when we talked about block ciphers, we saw a general attack on block ciphers which we called exhaustive search, and that attack forced the key size for a block cipher to be 128 bits or more. Similarly, on collision resistance, there's a general attack called the birthday attack, which forces the output of a collision-resistant hash functions to be more than a certain bound. And so let me show you the attack, and then we'll see what those bounds come out to be. So here's a general attack that can work on arbitrary collision-resistant hash functions. So here we have our collision-resistant hash function, supposedly. Let's suppose that it outputs n bit values. In other words, the output space is roughly of size 2 to the n. Now the message space is going to be much, much larger than n bits. Let's just say that the messages that are being hashed are, say, 100 times n bits. I want to show you an algorithm that can find a collision for this hash function h in time roughly 2 to the n over 2. Okay, so roughly the square root of the size of the output space. So here's how the algorithm is going to work. What we'll do is we'll choose random 2 to the n over 2 messages in our message space. Let's call them m1 to m2 to the n over 2. Now, because the messages themselves are much bigger than n bits, they're 100 times n bits, it's very likely that all these messages are distinct. So they'll be distinct with high probability. But for each one of these messages, we're going to apply the hash function and obtain a tag t sub I. So this is, of course, the t sub i's are n-bit long strings. And now we're going to look for a collision among the t sub i's. In other words, we're going to find an I and a j such that t sub I equals to t sub j. And once we've done that, we've basically found a collision because, as we said, with very high probability, mi is not equal to mj, but the hash of mi is equal to the hash of mj, and therefore we found a collision on the function h. Now, if it so happens that we look through all 2 to the n over 2 t sub i's and we don't find the collision, we go back to step 1 and try another set of 2 to the n over 2 messages. So the question is, how well will this work? In other words, how many times do we have to iterate this process until we actually find the collision? And I want to show you that, in fact, the number of iterations is going to be very, very small, which means that this algorithm will find the collision in time that's roughly proportional to 2 to the n over 2. So to analyze this type of attack, I have to tell you a little bit about the birthday paradox. I imagine some of you have already heard of the birthday paradox. Here stated as a theorem, and I want to prove it to you because everybody should see a proof of the birthday paradox at least once in their lives. So here it is. So imagine we have n random variables, r1 to rn, in the interval 1 to b. And the only thing I'm going to assume about them is that they're actually independent of one another. That's crucial, that these n samples, r1 to n to rn, in this interval are independent of one another. And they also happen to be distributed identically. So for example, they might all be uniform in the interval 1 to b, but again, these would be independently uniform variables. Now, it so happens that if we set n to be about the square root of b, in other words, if we sample roughly square root of b samples from the interval 1 to b, to be precise, it's 1.2 times the square root of b, then the probability that 2 of those samples will be the same is at least a half. Okay, and then it turns out, in fact, the uniform distribution is the worst case for the birthday paradox. In other words, if the distribution from which the ri's are sampled from is non-uniform, then in fact fewer than 1.2 times square root of b samples are needed. The uniform distribution is the worst case. So we're going to prove this for the uniform distribution, and that basically just also proves it for all other distributions. But the proof that I want to show you here will hold just for the uniform distribution. Okay, so let's do the proof. It's actually not difficult at all. So we're asking, what is the probability that there exists an I that's not equal to j such that Ri is equal to Rj? Well, let's negate that. So that's basically 1 minus the probability that for all I not equal to j, we have that Ri is not equal to Rj. This basically means that no collision occurred among the n samples that we chose. Well, let's try to write this out more precisely. Well, we're going to write this as 1 minus. And now when we choose R1, basically it's the first one we choose, so it's not going to collide with anything. But now let's look at what happens when we choose R2. When we choose R2, let me ask you, what is the probability that R2 does not collide with R1? Well, R1 takes 1 slot, so there are b minus 1 slots that if R2 falls into, it's not going to collide with R1. So in other words, the probability that R2 does not collide with R1 is b minus 1 slots divided by all b possible slots. Similarly, when we pick R3, what is the probability that R3 does not collide with either R1 or R2? Again, R1 and R2 take up 2 slots, and so there are B minus 2 slots that remain for R3. If it falls into either one of those B minus 2 slots, it's not going to collide with either R1 or R2. So I imagine you see the pattern now. So R4, its probability of not colliding with R1, R2, or R3 is B minus 3 over B, and so on and so forth until we get to the very last Rn, and the probability that Rn does not collide with the previous Ris, well, there are n minus 1 slots taken up by the previous Ris. So if Rn falls into any of the remaining B minus n plus 1 slots, it's not going to collide with any of the previous R1 to Rn minus 1. Now you notice the reason I was able to multiply all these probabilities is exactly because the Ris are all independent of one another. So it's crucial for the step that the Ris are independent. So let me rewrite this expression a little bit. Let me write it as 1 minus the product of I goes from 1 to n minus 1 of 1 minus I over b. Okay, all I did is I just rewrote this as a big product as opposed to writing the terms individually. So now I'm going to use a standard inequality that says that for any positive x, 1 minus x is less than e to the minus x. And that's actually easy to see because e to the minus x, if you look at its Taylor expansion, is 1 minus x plus x squared over 2 minus and so on and so forth. And so you can see that we're basically ignoring this latter part of the Taylor expansion, which happens to be positive, and as a result, the left side here is going to be smaller than the right-hand side. Okay, so let's plug this inequality in, and what do we get? We get that this is greater than 1 minus the product of I goes from 1 to n minus 1 of e to the minus I over b. Okay, I simply plugged in x equals I over b for each one of those terms. Now the nice thing about exponentials is that we multiply them, the exponents add. As a result, this is simply equal to 1 minus e to the power of, here, let me take the 1 over b out of the parentheses, sum of I goes from 1 to n minus 1 of I. Okay, so all I did is I took the minus 1 over b out of the parentheses, and we're left with a simple sum of 1 to n minus 1. And so the sum of the integers from 1 to n minus 1 is simply n times n minus 1 over 2, which I can bound by n squared over 2. And so really what I get at the end here is 1 minus e to the power of minus n squared over 2b. Okay, I literally bounded this sum here by n squared over 2. Okay, very good. Now, so what do we know about n squared over 2b? Well, we can derive exactly what n squared over 2b is from the relationship here. So if you think about it, let's look at n squared over 2. Well, n squared over 2 is 1.2 squared over 2. 1.2 squared is 1.44. Divided by 2 is 0.72 times the square root of b squared, which is b. Okay, so n squared over 2 is 0.72b, and as a result, n squared over 2b is just 0.72. So we get 1 minus e to the power of minus 0.72. Well, so now you just plug this into your calculator and you get 0.53, which as far as I know is always bigger than a half. So this proves the birthday paradox, and you notice it was crucial to assume that the samples are independent of one another. We only proved it for the uniform distribution, but as I said, it's actually fairly easy to argue now that any distribution that's away from the uniform distribution will satisfy this with even a lower bound. So if you have 1.2 square root of b, the theorem will certainly hold for non-uniform distributions. The reason it's called a paradox is because it's very paradoxical that the square root function grows very slowly. In particular, if you try to apply this to birth dates, so let's assume that we have a number of people in a room, and let's assume that their birth dates are independent of one another and are uniform in the interval 1 to 365, then what the birthday paradox says is that we need roughly 1.2 times square root of 365, which I believe is something like 23, which says we need roughly 23 people in a room, and then with probability 1/2, 2 of them will actually have the same birthday. The reason it's called a paradox is because the number 23 seems really small to people, and yet by this theorem that we just proved, with probability 1/2, there will be 2 people with the same birthday. By the way, the intuition for why this fact is true is because really what the collision is counting is it's looking at all possible pairs of people, and if you have a square root of b people, then there are square root of b squared pairs, roughly, which is roughly b pairs total, and so it's very likely that each pair collides with probability 1 over b, and if you have b pairs, it's likely that one of the pairs will collide. So hopefully this gives you intuition for where the square root comes from. It's basically from the fact that if you have n people in a room, there are n squared possible pairs. I should say, by the way, that even though the birthday paradox is often applied to birth dates are actually not uniform at all. If you actually look at the birth dates of people, you see that there's a very clear bias towards being born in September, and for some bizarre reason there's also a bias towards being born on a Tuesday. And so when we apply the birthday paradox to birthdays, in fact the actual bound is going to be smaller than 1 minus 2 square root of b, because we said that for non-uniform distributions you need even fewer samples before you get a collision. So let me show you a graph of the birthday paradox. It's quite interesting how it behaves. So here I set b to be 1,000,000. In other words, we're picking random uniform samples in the range 1 to 1,000,000. And the x-axis here is the number of samples that we're picking, and the y-axis is the probability that we get a collision among those n samples. So we see that the probability of 1/2 happens around 1.2 square root of b, roughly 1200, 1.2 square root of b. And you see that if we look at exactly square root of b, the probability for a collision is around 0.4 or 0.41. And you notice the probability goes up to 1 extremely fast. For example, already at roughly 2 square root of b, the probability of a collision is already 90%. Similarly, when we go below square root of b, the probability of a collision very, very quickly drops to 0. Okay, so there's kind of a threshold phenomena around square root of b, where the probability for a collision goes to 1 very quickly above square root of b, and drops to 0 very quickly below square root of b. So now we can analyze our attack algorithm. So let me remind you, here we chose 2 to the n over 2 random elements in the message space. We hashed them. And so we started off with a random distribution in the message space. After we hashed them, we end up with some distribution. This distribution over tags might not be uniform, but we don't care. The point is that all these tags, t1 to t2 to the n over 2, are independent of one another. And as a result, if we choose 2 to the n over 2 or 1.2 to the n over 2 tags, the probability that a collision will exist is roughly 1/2. So let me ask you then, in that case, how many times do we have to iterate this algorithm before we actually find a collision? Well, so since each iteration is going to find a collision with probability 1/2, we have to iterate about 2 times in expectation. And as a result, the running time of this algorithm is basically 2 to the n over 2 evaluations of the hash functions. Okay, so notice also this algorithm takes a lot of space, but we're going to ignore the space issue, and we're just going to focus on the running time. Okay, so this is kind of cool. This says that if your hash function outputs n-bit outputs, there will always be an attack algorithm that runs in time 2 to the n over 2. So for example, if we output 128-bit outputs, then a collision could be found in time 2 to the 64, which is not considered sufficiently secure. Okay, so this is why collision-resistant hash functions generally are not going to output 128 bits. So let me show you some examples. The first 3 are actually federal standards, SHA-1, SHA-256, and SHA-512. And the fourth one is an example from the designers of AES called Whirlpool. And so you can see SHA-1 outputs 160 bits, and as a result there's a generic attack on it that runs in time 2 to the 80. SHA-256 outputs 256 bits, so the generic attack will run in time 2 to the 128, and so on and so forth. I also listed the speeds of these algorithms, and you notice that the bigger the block size, actually the slower the algorithm is, and so there's a performance penalty, but nevertheless there's quite a bit of benefit in terms of security. Now you notice the SHA function is actually grayed out. The SHA function, although nobody has found collisions for SHA-1 yet, it's still recommended that in new projects and hopefully in programming projects in this class, you don't use SHA-1, instead use SHA-256. And in particular, there's actually a theoretical collision finder on SHA-1 that works in time 2 to the 51. So it's probably just a matter of time until finally someone finds a collision for SHA-1 and just kills altogether. But the current advice is SHA-1 is still a collision-resistant hash function because nobody has found collisions for it, but it's probably just a matter of time, just a few months or a few years until a collision is found. And as a result, in new products and new projects, SHA-1 should not be used and only use SHA-256, or if you want to be even more cautious, then use SHA-512. So this is the end of this segment, and now we're going to turn to building collision-resistant hash functions.